Hello everyone, welcome back to lesson 16. We're talking about the fundamental theorem of calculus, and we're now going to look at these problems with trig functions. So very basic stuff with the next couple of examples here. It says find the area under the curve, the cosine curve, from 0 to pi over 2. So area under the curve is the same thing as the total change. So from 0 to pi over 2, we're going to integrate the cosine function. Right, we're going to integrate the cosine function. So all we do to integrate cosine, we're going to get sine of x, and since it's the fundamental theorem and we actually were looking for a value, then we're going to evaluate that from 0 to pi over 2. So that's going to give us the sine of pi over 2 minus the sine of 0, and then the sine of pi over 2 is going to be 1 minus the sine of 0, which is 0. So the area under the curve of the cosine function from 0 to pi over 2 is simply going to be 1. Okay, so there'll be a lot more examples of this in the next lesson that we talk about, but this is the idea. As you guys are seeing in this particular lesson and these examples I'm doing for you, it's what we've been doing in previous lessons. Just now I'm incorporating trig functions, right? We're just integrating trig functions. Question number 2 is a fundamental theorem part 2 question, right? Fundamental theorem of calculus part 2, where you do the same thing. We want to find the derivative of an integral. So remember, when we're taking the derivative of an integral, that's the fundamental theorem of calculus part 2. This is where we take our 3x and we're going to go ahead and plop it down everywhere we see a t. So we're going to get the g prime of x is going to be equal to 1, the square root of 1 plus sine of 3x quantity squared. Remember, we have to square the 3 as well. We have to square the 3 as well. And then we also have to multiply by the derivative of what we plug in here, right? So that's the two big key factors that people forget when we're doing this is we have to square the 3 and the x, right? Not just the x. And we also have to multiply by 3. Now we would continue on with this problem if we wanted to. And remember, for a constant, we've actually already had this conversation in a previous video, but it'd be minus, right? It's f of b minus f of a. You do the same thing. You plug in 0 to your function. You'd square it, but then you have to multiply by the derivative of your 0, right? The derivative of 0 is just 0. So then whenever we have a constant, we don't have to worry about that. So this answer is going to be 3 times the square root of 1 plus sine of 9x squared. Okay, 9x squared. So we're not really integrating this. We're not doing u sub or anything like that. We're just going to use fundamental theorem of calculus part 2. For example number 3, it's asking us to find the derivative again of an integral. And so just like the previous example, notice for both of these, we actually have functions here. So I'm going to go ahead and take the 3x to the 5th, and I'm going to plot it down. So I'm going to get equals the cosecant of 3x to the 5th, right? And then I'm going to multiply by the derivative of what I'm plugging in, right? So the derivative of 3x to the 5th is 15x to the 4th. Minus, and now I'm going to take the x, I'm going to plug it in, just plop it in there. So I'm replacing the t with x, and then I got to multiply by the derivative of x, which is going to be 1. So this answer is going to be 15x to the 4th cosecant of 3x to the 5th minus cosecant of x. Okay? All right, so let's go and do one more fundamental theorem of calculus problem. It's going to be question number 5. And so for this particular example, it's asking us to find the area under the curve, and it's given us that this curve right here is part of the 3x squared, and that this curve right here is y equals negative x plus 4. So this is not a trig question, but it is just really helpful. So we want to integrate from 0 to this value right here of 3x squared dx. And so how do we get this value? Well, we simply set these two things equal to each other. Right, and then we're just going to factor. So we're going to bring the x and the 4 over. And we're going to factor this guy just to see what we can have here. So it looks like this would be a 4, and this would be a 1. So this would be positive and negative, right? So we get x is equal to negative 4/3, which we don't care about, and x is equal to 1. So from 0 to 1 of x, 3x squared dx. And then we're going to integrate from 1 to this value right here of negative x plus 4 dx. And again, how do we solve that? Well, in this value, y is 0. Y is 0. So we get x is equal to 4. So we're going to go from 1 to 4. of negative x plus 4dx. And then we just integrate, right? We're going to integrate by hand here, so it's going to be 3x cubed over 3, evaluate it from 0 to 1, and then we're going to plus, we're going to integrate negative x is negative x squared over 2. The integration of 4 is just 4x, and we're going to evaluate this from 1 to 4. And, you know, the 3's are actually going to cancel out, so this is going to be left with 1 minus 0. So this part right here is just going to be simply 1. And then this right here is going to be, well, 4, right? 4 goes in the 4 squared, 16. 16 divided by 2 is going to be 8. So this is going to be negative 8 plus 16. And then minus, be careful, remember f of b minus f of a. We're going to plug in 1 here, or we're going to get negative 1/2. And then we're going to get plus 4. And after all is said and done here, we're going to go ahead and get, this is going to be 8. And this is going to be, what? 7/2. So minus 7/2, which is going to be 3.5. And so we get 9 minus 3.5 is 5.5. Is that the answer? That looks good enough to me. So 5.5. The answer is 5.5. So that was, again, just an example of just basic integration where we had to find our values of integration 1 and 4. All right. So the last thing we're going to do in this video is a really awesome FRQ, and I really like it. And it talks about the fact that the function here, g of x, well, let's read the question. It says the graph of a differential function f on the closed interval from -3 to 15 is shown in the graph below. So this is f of x. So this graph right here is f of x. The graph of x has a horizontal tangent at x equals 6. So we have a horizontal tangent right here. And it gives us actually a function for g. It tells us what g is. G is equal to 5 plus the integration of 6 to x of f of t dt. So this little guy right here actually helps us bridge how to relate g and f. So here at the bottom, it's going to ask us to find g of 6, g prime of 6, and g double prime of 6. So g of 6, we literally plug in. So I'm going to put a right here. So g of 6 is going to be equal to 5 plus 6. And again, we're evaluating. So everywhere we see an x, we're going to put another x. Or sorry, wherever we see an x, we're going to put a 6. So we're going to put a 6 here, and there's going to be a 6 here of f of t dt. So one of the properties you guys learn here is if I'm integrating from 6 to 6, or 5 to 5, or 4 to 4, whatever, this is 0, right? There's no area here. There's no total change. There's no total change from 6 to 6. So I know that g of 6 is simply going to be equal to 5. So there's our first little part. Now the next part is very interesting. I want to find the derivative of this, right? I want g prime of 6. So the derivative of g of x, well, the derivative of 5 is 0, so we're good with that. So we're finding the derivative of an integral, right? And so just like in the previous example I just did earlier in this video, Fundamental Theorem of Calculus Part 2, I'm going to take the x, I'm going to plop it down, and I'm going to get f of x times the derivative of x, and then again, with the constant, I don't have to worry about it. So this is a really powerful statement, and sometimes you guys get a point for this, that the derivative, so this is not only the graph of f of x, this is now the derivative of g. So we have a derivative graph. So if I want to find what g prime of 6 is, I want the derivative, well, I want what is f of 6, right? So g prime of 6 is just equal to f of 6. Well, f of 6 is going to be equal to 3. So I now know that g prime of 6 is going to be equal to 3 because, again, I have a relationship of derivative. The derivative of g is equal simply of f of x. And then our last part of this problem for a is I want to find the second derivative. So the second derivative of g is the first derivative, and I should actually have an x right here. It's going to be the first derivative of f. So what's the derivative at this value right here? Well, we've already said we have a horizontal tangent at x equals 0. So, sorry, at x equals 6. So g prime of 6 is the same thing as f prime of 6, which we know that the slope of the tangent line at 6 is going to actually be 0. So our second derivative is actually going to be 0. Okay? So that's how you do these problems. That's how you do this problem right there. So simply plug in to find g of 6. find the first derivative of our function here. Again, the 5 goes away, and we use the fundamental theorem of calculus part 2 to figure out that g prime of x is equal to f of x. And then finding the second derivative is just the first derivative of f, which again would just be the value of the slope of the tangent line or whatever we want to do with that problem. It says, on what values is g decreasing? All right, so g, remember, this is the derivative of g right here. This is the derivative of g. So where is g decreasing? It's decreasing here because g prime of x is less than 0. It's also decreasing here. Right, it's also decreasing here. So the interval, so for part B, I'm writing everything up here, I like it. It's going to be from -3 to 0 and from 12 to 15. And the reason why, ladies and gentlemen, is that g prime of x is less than 0. Right, this value, this slope is negative, right? These are the slope values. So if we're negative down here, then we're going to be decreasing. So hopefully that makes sense for that particular problem. Justifying your answer is the fact that g prime of x is less than 0. On what intervals is the graph concave down? So g concave down. So for concavity, we have to look at the second derivative, which is the first derivative of this graph, right? So where are we negative? Where's our slope negative? So from -3 to 6, we're increasing, right? We're going up. But from 6 to 15, we're actually going to be decreasing. So we would say that f prime of x is decreasing, or we would say that g prime of x is less than 0. Right, so we're looking at the slope for this one. So for part C, it's just asking us, what intervals is g concave down? Remember that concavity is a second derivative, and so it's the slope of our slope, right? In this case right here, it's the rate of change of our change. And then the final one is, now I'm not doing the trapezoidal thing. So that's really all I care about for that. The trapezoidal thing, we can do that later in life. I don't care about that one. So hopefully that makes sense to everyone, and this is where we're going to stop the video. And I will see you guys in our next lesson when we start talking about more integration of trig functions.